Is it true that you are working on forbidden science?
Well, I don't know that it's forbidden. Certainly, people know I'm doing it, or that we are doing it, and no one has told us to stop. Now, there may be some in the scientific community that feel like it's stupid science. I don't know if that's the same as forbidden, but so no, I'm not sure. I don't think we're working on forbidden science. But
I mean, in terms of, like, and I won't mention any names, but or groups, but there are a lot of people that are very afraid to work on this, and they are afraid of people suggesting that they are working on wrong science.
Yeah. I think initially it was a credibility issue. Anybody who's dumb enough to work on this is going to bring damage to the credibility of our organization. And I think that was a concern early on. I don't believe it's as bad now as it was. Say the early years it was okay. The report came out from the Department of Energy that said, we don't think it's worth investing any money in at this point, but it was kind of inconclusive. So in the early years, actually the Navy did spend some money working on it. There was a study done with people from NRL, China Lake, and ourselves in San Diego. And so at that point in time, we were trying to discover what is going on. And Fred Sawfeld was the senior civilian at ONR at the time, and Fred had the nerve to continue to fund this area. I haven't talked to Fred directly, but in one of the interviews that he gave, he said he stopped funding it because he would go to meetings and people from ONR would come back from meetings and say that ONR and the Navy is the brunt of jokes because they're continuing to fund research in cold fusion. So that, plus I think Fred was concerned that ultimately it could impact the budget at ONR, caused him to say, we need to terminate funding in this area. So I don't think he terminated from a scientific standpoint because the questions were still there. I think he terminated because it was he was concerned it was going to have detrimental impact on all of the Office of Naval Research.
Were you concerned? Were you worried about the image?
We were doing good science in my book, and by that I mean we did experiments, we recorded the results, we published those results in scientific peer-reviewed journals. That's the scientific process. That's the way it's supposed to be done. So we always had that to lean back on. If someone would have come to us and said, you shouldn't be doing this, we could have said, well, tell us what we shouldn't be doing. Here are results, here are experiments that we did, here are results that we got. We published those results in a peer-reviewed journal. And now, that was the defense that I had planned in the event that the questions were asked. I'm glad that the questions weren't asked in those days because, well, now, 19 years later, the results we have are much more compelling. So, at this point in time, I think if someone came and accused us of doing fraudulent science, the results would speak for themselves.
So what's your perception of the climate of this field today?
Interesting. I think now the people who are concerned maybe are the ones that have were critical and trying to discredit anyone working in the field for all these years. I think now they're perhaps a little bit concerned because the data is on our side. The data is out there saying if you do this experiment, these are the results you get. Oh, by the way, the experiments we've done are repeatable. We've repeated them several times. Oh, by the way, others have replicated our experiments. Oh, by the way, the data that we're seeing are multiple sets of data and results that lead one to believe that this is anomalous, that there's something going on here. And recently, the data is saying, and it is nuclear. And so over time, now they wouldn't just be arguing with one set of data. In the case of Pons and Fleischmann, they had a few sets of data, but it was incomplete, it wasn't reproducible, it hadn't been peer-reviewed. All of those things have changed. In addition, it's not just ourselves who've done this. There are groups of people in Japan, in Italy, other groups here in the U.S. who have continued to work in this area, and no one is doing the experiment exactly the same way as the other people. If all scientists want to add something, and so if you give them a recipe and say this is how to do the experiment, you can bet they aren't going to do it that way, because they will figure out a way to do it better. So multiple approaches to investigate this area, and I'm casting a rather broad net now on what this area is, but multiple approaches are producing similar results. For example, in Japan, they're showing transmutations, and they're seeing aluminum and calcium and magnesium and things like that. The way they're doing the experiments is a gas diffusion through a membrane. In our case, we're seeing similar results, similar end products, aluminum, magnesium, and so on, as a result of a co-deposition experiment done in either an electrostatic or a magnetic field. George Miley at one time compiled a list of numbers of people in labs that are reporting transmutation and what their products are, what the products of transmutation are. And it's over a dozen different organizations throughout the world who are seeing the same kinds of transmutation products. Now, is it all related to the cold fusion phenomena? I don't think we know, except that it is in one way, and that is that it is a nuclear reaction that wasn't predicted or expected based on conventional understanding.
I have a question. It may not be a fair question, but
Okay.
if you want to try and answer at it or explain why it's a difficult question, your choice. How would you describe cold fusion, or what is what is cold fusion? If people ask you, how do you attempt that?
Well, I guess the short answer is it's confusion, because there's a lot of confusion. It seems to, I think now, if I were to describe it, I would say it's that set of experiments that lead to what appears to be nuclear results that aren't predicted by conventional nuclear theory. Conventional nuclear theory would not lead you to believe that you could input 2 or 3 volts into an electrochemical cell and get nuclear products out, which typically take a minimum of 1 million electron volts to stimulate. So where does that energy come from? This was one of the big questions that physicists have always had, is where did that come from? The electrochemists in the group will tell us that there are layers within the palladium cathode where you have this very high current densities, and so maybe there are areas that can occur in, but this is not something that is understood. It certainly was not part of conventional physics theory for nuclear reactions.
What about your? You have some recent papers that talk about the results from your experiments with the co-deposition. How's the publishing and the peer review papers gone for you, your group?
Okay. Actually, we've published, I think the count is 19 papers now. We have a couple more that are in the process somewhere and are working on a couple more. Our papers roughly, cover from the very beginning where we saw the electrode was hotter than the solution, to papers describing the X-rays that we saw when we took an electrode after the experiment and laid it next to some photographic film, and it caused the photographic film to fog. to transmutation measurements that we conducted, to observing the electrode with an IR camera and seeing these flashes of hot spots as they were occurring. We then did some measurements with acoustics where we actually co-deposited right onto a transducer, right on the face of a piezoelectric transducer, and then recorded the events as they were occurring, and this provided another real-time opportunity to look at the events as they occurred. We published papers on our cyclic photometry. We've published papers on the transmutation that have occurred, and then more recently we've published papers using CR39 to record nuclear events as they're occurring in the cell.
What's your now the two questions? One is the journals that you've published these papers in. Are they normal science journals, or are they kind of off the beaten path? Are they legitimate peer-reviewed journals?
Yes, they're legitimate peer-reviewed journals. Early on, we published some papers in some of the physics letters journals. Lately, they have not been as receptive, but we have published several of our recent papers in Naturwissenschaften, which is a German technical journal that has been around for well over a century. Einstein, Niels Bohr, Max Planck, all of these people have published in that journal. Certainly that is not one that you would call a fly-by-night or a less than reputable journal. So we have worked very hard to make sure that we've published in these journals, and I'm sure we've caused some heartburn for some of the editors of those journals when we submit our papers.
What's the process been like? Easy, difficult?
I think the transmutation paper was in review for over 7 months. And in that paper, they came back several times and said, well, how do you know it's not contamination that led to these results? And fortunately, we had kept samples of the solutions and everything. So we knew the pedigree of the chemicals. We could go back and say, we bought these chemicals and this was the lot number, and the chemical companies keep records of the purities, and so we knew the pedigree of the chemicals. We had kept samples of everything, and then we just kept, so they would ask a question, we'd respond. They'd ask a question, we'd respond, and ultimately the way we answered the contamination issue was when Stan Spock pointed out to them that even if we had put dissolved aluminum in the solution when we started, it would not have co-deposited out. And at that point, they decided to publish the paper.
What journal?
Naturwissenschaften.
You have two papers in Nature, or just one in Naturwissenschaften?
We have a transmutation paper, I think that was in Naturwissenschaften, and then the CR39 paper in Naturwissenschaften. I believe both of those were Naturwissenschaften.
And you have a recent paper in physics review?
I don't believe so.
What's the last paper that your group had? PRL? EPJ, European Physics Journal.
Yes, European Physics Journal. Was that the CR39?
Further evidence. I think it's
okay.
Further evidence of something. I think it was in the European Physical Journal.
Yeah.
Okay.
So all of these are, these are certainly reputable peer-reviewed journals.
So your position relative to the research has been how?
Okay, well, in 1989, I headed the anti-submarine warfare department at our lab, and we were involved in developing lightweight torpedoes, which is, at the time, we were doing research to see if we could develop a battery propulsion system for the torpedoes. And that meant I had electrochemists like Stan Spock and Pam Voss in the department. So when the announcement came out, and Stan already knew Flashman, they figured out very quickly, and being having worked in batteries and electrochemistry, developed the co-deposition process. And so at that point, they were funded by internal funding at the laboratory. They wrote a proposal and received internal funding. So I was basically a hands-off department head at that point. Then I left in the early 90s to go be the executive director at another organization, another Navy lab here in San Diego. And during that time, I think a lot of the research kind of died in this area. Stan retired. There wasn't, the internal funding went away. There wasn't any external funding. And as a result of another base realignment and closing action, the organization that I was the executive director of was merged back into the lab that I had come from, and I ended up as a department head, and I had my scientists and physicists working for me again. So at that point I called Pam and asked her what was going on in the cold fusion research, and she said, well, it basically had, nothing was being done. This was in the mid-90s. So I called Stan. He was at home, and I asked him if he was still interested in this, and he said yes. And I said, well, how would you like to come back to work where you set your hours, where you can work on what you want to work on, and you don't have to write proposals? And he said, well, gee, that sounds great. And I said, the reason I'm going to offer you that deal is because I'm not going to pay you. And he said, well, I'm retired, I don't need it. So I said, all right. So the deal basically was I provide Stan with an office and in the lab, and buy a minimal amount of chemicals and things like that using overhead that I have, so that we can continue to conduct experiments. Pam is funded working on other projects, or has been funded working on other projects, but we all would come in early in the morning, or Saturdays and weekends and holidays, to work on what at the time was our hobby, cold fusion, and so that's how we kept it going. And now, more recently, because of the results we've gotten, we are now beginning to get funding again from our internal research funding program.
Full circle, amazing. Go back to the mid-90s for a moment. The mid-90s was relatively kind of a low point in the history of cold fusion. There was the Tri-Navy program that it had funded and that completed. There was a program in Japan that phased out. So you had this shift in your positions. You came back and you called up Pam and Stan, and you encouraged them to get back in. Where did you have the inspiration, insight, whatever, to try to get this going again? Where did that come from?
That in my mind, something was going on. Before I left in the early 90s, we had done enough experiments to convince me that something unusual is happening. And it starts out, I was thinking of this the other day, it starts out with the simplest of experiments. The very first experiment where the electrode heated up hotter than the solution. And, to a lay person looking at a chart of that or a graph of that, they would say, ho hum, well, that's, what is so interesting about that? But the thing that was interesting about that is not what was predicted. What would have been predicted was the solution should have heated up hotter than the electrode. So just finding the answer to that kind of started this process that leads us where we are today. And when I left in the early 90s, we didn't know the answer. When I came back, I wondered, did anyone ever solve that? Where are we? What happened? And discovered that no, it was still there. And so it was a challenge. I guess And it was an opportunity. Not everybody gets a chance to answer a question in fundamental science. And in this case, if we can answer this question, the impact as an potential energy source, a whole host of other applications are huge. And so just the opportunity to work on something like that is, I think, what got me back into it. And as the results now continue to compound, to where the evidence is, in my mind, beyond question. Now, I guess you can always question anything, but that nuclear events are occurring. That in itself is something that just needs to be investigated. We need to understand this.
Did the public perception of the subject ever have much of an influence on you?
The public's perception didn't really have that much. If you want your teenage son not to do something or to do something, tell them that they can't do it, and then what they'll do is they'll focus all their energy on proving you wrong, and so maybe there was some of that involved. People were saying you can't do it, and so clearly you need to prove them wrong and spend some time doing it. But as far as my personal interaction and why did I get involved in it, in a lot of ways it was therapy. I think I'm getting more out of this than anything I'm putting in. If it weren't for this, I would spend all my days in meetings, which I do now anyhow, but at least in my own hours now I can work on something like this, which is therapy. And I've got other projects and people that work in my department that are brilliant people, and if I can run interference for them, if I can help them get some funding, if I can help them with getting it into an application, the payoffs are huge. And again, the payoffs not only for the Navy are huge, but for me personally, as far as therapy, they're huge. I've been eligible to retire for 7 years, and I still get up early in the morning and go in, and it's not because I want to go into all those meetings. It's because I could go in and work with people like Stan Spock and Pam Boss and people working in an area of nonlinear dynamics, which is another area that I spend a lot of time on, that I think also is going to have huge payoff.
So the climate's shifting. You've been able to garner some internal funds now.
I think it's shifting a lot. I still don't want all the media attention that showered down on Pons and Flashman. If you read the books of what happened in that time frame, they were really scrambling. They had done these experiments, they had observed the results. They just didn't have any of the answers that people were asking them about. And in some cases they speculated, and their speculations turned into statements that maybe weren't fully supportable, and maybe even the statements weren't made by them, but others that made statements that said they had said, and so it became a real circus and out of control, an event that they couldn't control. Early on, I was concerned that might happen, and were we able to do that? And what I had told my supervision was that all we were doing was reporting our results in refereed peer-reviewed journals. And so that was, whatever backup I had or explanation I would have had if the spotlights would have been turned on us and said, why are you wasting money working in this area? I would have said, well, look at the data. The data is the data. There's a statement that theory guides, but experiment decides. So if you have a theory that says one thing and an experiment that says something else, you can adjust the theory, The experimental results are what they are, and you can't adjust those. And so the fact that there were theories out there that were in conflict with our results, it means the theorists have to change, because the results are what they are.
Do you have any thoughts about this fear that people have about talking about this, about doing this work, just people being afraid?
Well, certainly you could be subject to criticism, and that might hurt your ability to get funding not only in this area but in other areas. The critics, and there are fewer of them now than there used to be, are largely going on old data. And in fact, it's kind of interesting. We haven't gone out looking for publicity in what we've done. We've published our papers in refereed journals. We've made a couple of presentations at one of them was an ONR sponsored technology symposium. Another was an NDIA, National Defense Industrial Association symposium that had a breakout session on energy, and we presented there. A couple of magazines have done articles on us. And interestingly enough, the skeptics have been quiet. I don't know what they're saying behind our backs, but they don't seem to be as willing to come out and challenge us at this point. And I think if they did, they know that our answer would be, we did this experiment and these are the results we got. So don't attack us, for doing the experiment and getting these results. Tell us what we're doing wrong. In fact, I jokingly commented to someone, I said, if we're doing something wrong, I wish they'd tell me so I can get on with the rest of my life. Because right now, this is something that I'm trying to understand.
So do you think there's remains any legitimate reason to be afraid to work in the subject matter?
Well, I think it's still a legitimate issue that funding could be an issue. Certainly DOE, as recently as 2-3 years ago, they did another look at it, and their report was really interesting. Of the 15 or 16 or so experts that looked at it, it was almost a bell curve. There were some that said, absolutely, there's fusion going on here. We need to program this. There were others that said, no, I don't see anything new. And there were a large group in the middle that said, this is kind of interesting. And the fact that any experiment is out there that contradicts theory, that isn't predicted, you would think the Department of Energy would want to fund it, to find out what is going on here. But even after this report came out, the second report, they still haven't funded it. And I guess I will point out that there were limitations put on what could be presented in that report, focused mostly on heat, excess heat. And we have far more compelling evidence of nuclear reactions now.
What would you like to say to Congress, to DOE, all of them, about this?
Well, actually, it's not what I would like to say, but what is the data saying, and have they reviewed the data? My feeling is that they probably haven't. I know of reporters who've talked to people who were among the initial skeptics, and when they talk to them again, they say, well, I haven't seen anything new. And they say, well, have you reviewed anything? And then it starts skating around a little bit, and ultimately it's pretty clear they haven't reviewed anything. And so then when you ask, well, would you be willing to review something and give me your input, then no, I don't have time. So I think the initial skeptics are, at this point, if they've been following the field at all, they know the data is out there, that should cause some concern on what their theory is. So it's really not what I would say to them, but It's what would the data say, and I think the data would say that there's something going on here that we need to understand.
So about those skeptics who you say have been asked, well, would you look at the new data? Would you expect them to say, to come forward and say, well, well, we were wrong?
No, I don't know who made this quote, and I probably don't have it right, but there's a quote that says science progresses one tombstone at a time, or something like that, and the implication being that the only way you ever change is when somebody dies, then the new ideas can come along. And you know, I will say that, you know, we've had college students at, you know, replicating some of our experiments here at UCSD. Maybe we're potentially doing permanent harm to their career by having them work in this area, but I don't think so. They are excited about it. To them, this is a question that they would like to get involved with in answering. So, no, I'm not going to hold my breath that some of the skeptics are going to come around and say, no, we were wrong, or this, you know, for them to change their mind. I think they would rather, at least in this area, evaporate into obscurity rather than come forward and admit that maybe they were wrong when they made their initial assessment. You know, I'm not a scientist, so I don't have a science career that I'm trying to protect. So it's easier for me perhaps to get involved in working in this. Although I had a hotline complaint filed against me anonymously by someone who claimed that I was wasting government money by spending some of my overhead to work in this area, to buy chemicals and you know, instrumentation and things like that, probably a few $1,000s a year. I never actually saw the hotline complaint. I wish I had it because I would like to frame it. But the reason I never saw it was the admiral at the time, our admiral at the time was Admiral Jack Donegan, and he looked at it and said, this is crazy. Frank is a department head. As a department head, he manages X number of people and a budget of this big, and because of that, he has discretionary funds for bid and proposal work, and this could be spending money to develop a new work area. So he basically responded to the complaint, and before I even knew it happened. So that's, I think that's an example of Navy leadership that maybe some organizations don't have, but in my case, it's been that way. Now, it's true they haven't funded us. You know, for years we've gone without funding, and that's not all bad. You know, if you don't have any money, then they can't take it away from you. So it makes them tougher to tell you what to do. The other thing is, you can figure out what you think needs to be done. If someone funds you, then they are probably going to tell you, okay, I want you to do this set of experiments. Well, maybe after you did one of those or something, you would determine, you know, I really need to do something different. And so if you're not being funded, then you can figure out what path to go down, which makes the most sense. You don't have to go rationalizing or justifying it to everybody every time you want to change a new path. You sit there, you make an educated guess, you bring the smart people together, you talk about the results, and then you pursue that. So it's actually also much faster. You don't have to go through a bunch of processes to change course and follow the path that the data is directing you into. You know, one of the things that's interesting is who is working in this area and who isn't working in this area. And you know, the people who are working in this area there are some academics, you know, tenured most likely. Many of them retired at this point because, remember, you know, this has been going on for 19 years, so many of them are retired at this point, who are working out again because of the challenge. there are a few commercial people looking into it, working in areas, but here, you know, this is not the kind of thing where I can go to a venture capitalist and say, you know, I'm going to produce a product for you, a commercial product, in 18 months or something like that, which is what they would like. The groups that are not working on it that I think are surprising are the DOE, Department of Energy, and related organizations. One of the fears that I think is out there is from the hot fusion community, who receive the bulk of their money from Congress. And that money is extremely tenuous. So it's, you know, Congress has been funding them for years and years, and the progress has never kept up to the schedule that they've promised. And the answer always seems to be farther away and more difficult than they've promised. So if Congress got the idea that there was another alternative, with a stroke of a pen, their budgets could be severely impacted in the hot fusion side. And so I think that's one of the reasons that for concern that they might have. Now, I think that's a valid concern. Is it justifiable? I would hope that Congress wouldn't cut their budgets until we knew more about this field. You know, this field is, you know, we currently don't have a theory that explains it. All we have are some strange results, strange experimental results, that I think offer compelling evidence that nuclear reactions are occurring, but are they enough reactions that we're ever going to turn it into something useful, or is it just going to end up being a laboratory curiosity? We don't know that yet. But we won't know it unless we get some significant funding and get teams working on it to try and answer that question. And so in the meantime, I think because of the fear that funds could shift away from the hot fusion community, we're not getting the support there. In fact, many of the people working in that area, I think, could contribute significantly to this, because that is, you know, they are nuclear physicists. And if they were able to sit down with the data with an open mind and look at it and say, what could be going on here, and not fear that their careers as a hot fusion physicist could be in jeopardy, or that the funding for their continued work in that area could be in jeopardy, I think we'd be far better off.
When Fleischmann-Pons started out with, they had a few different hypotheses. One was that it was a new kind of fusion, deuterium fusion. Another, what they said in their April 20 JEAC paper, was that it was possibly a hitherto unknown nuclear process or processes. Obviously, we call it the cold fusion field, colloquially. Formally, we call it the low energy nuclear reactions within the field of condensed matter nuclear science. From what you see and know from your position, is it important from your perspective whether or not it's fusion or some other hitherto unknown nuclear process?
Yeah. At this point, I'm not sure that we could say it's fusion. In fact, there may be evidence that we may be seeing forms of fission. It is important if it's a nuclear process. And the reason for that is the amount of energy that might be available if it's a nuclear process. If I burn something, I typically get the equivalent of 5 to 10 electron volts per atom. If it's a nuclear process, I can get several million volts, electron volts per atom that I can convert into energy. So that's, you know, the goal. That's also the dilemma that caused so much problem when Fleischmann and Pons announced their initial discovery. Was how can you go from chemical reactions, which are typically a few electron volts, to something that's going to be millions of electron volts. And recall when Pons and Flashman made their initial announcement, they said it must be a nuclear process because it exceeds what we can account for chemically. So they didn't have any real direct evidence of a nuclear process. They didn't have, where are the neutrons? Well, they thought they had seen neutrons, but couldn't substantiate it. Where's the other nuclear ash? They really didn't have any. All they had was, if I look at the energy out from the cell I put in, there's more energy coming out than I could account for if I burned all of the chemicals in there and converted them to energy at 5 electron volts per atom.
And the apparatus and it does that.
Yeah. So, but it wasn't direct evidence. Okay, that's changed now. Yeah, we have transmutations initially to tritium. We have X-rays. We have transmutations to several additional elements: aluminum, magnesium, iron, zinc, so on. And now we've got other evidence of using CR39, which is a plastic. It's the most commonly used in eyeglass lenses, but the physicists have used it for decades as a way to record the passage of an ionized particle. So if an alpha or a beta particle passes through that, it tears the plastic a little bit, and you can etch it, and in the process you will see a pit. So this is something that the nuclear physics community has been using for decades. We borrowed that at the suggestion of Oriani and a couple others, and all of a sudden we're seeing pits in the CR39. That we sent the CR39 then off to people in the hot fusion community to analyze and see, what do you see here? And so, we're not the experts in CR39 analysis, although we're getting better, but we sent the CR39, the little plastic chips, off to experts and had them take a look at them. And so that data is now much stronger that there are nuclear reactions occurring. We sent our chips to a university, noted university that's funded and working in the hot fusion world, and through a third party. And so they didn't know where the chips came from. And they sent an email back to the third party, the intermediary, and said, we see alphas that appear to be of this energy level and betas and so on. And then they said, and by the way, we see what was the source that illuminated this target, because we see many more pits than what we get in our experiments. And so I got a call from the guy saying, what do I tell him? And I said, well, tell them it's a Navy project that we're not prepared to talk about yet. And I'm not sure that they know to this day what it is that are producing these chips. Now, if they read any of the literature, they would see chips that are producing this sort of thing, and they would see it's published by a Navy lab in San Diego, so they would probably start connecting the dots, or connecting the pits, I guess, at that point. So anyhow, that's who. Now, the other person that we sent them to and have them analyzed are people who are now retired, but who worked in the field for a long time, and in fact wrote books on the analysis of CR39 and using the depth of the pits and the size of the pits and how they were formed. So we actually have not been doing the analysis of the CR39 ourselves. We prepare them. We set up the experiment. We put the plastic in the experiment. We run the experiment. We etch the plastic, and then we send it off and have other experts tell us what they see and how it compares.
The strongest piece of evidence that I'm aware of from that group of experiments that you have is where you have pits that show up not only on the front side, in front of the presumed source, which is the cathode, but also immediately on the backside, spatially correlated. Have you had anybody suggest any possible explanation for that other than the obvious one?
We've had a lot of people, when they see it, they say, well, this looks like some sort of a neutron burst or something like that, or some sort of a galactic event. And then you say, well, gee, how is it that this galactic event only hit the CR39 exactly in the spot opposite our electrode? And then we've had others who've suggested that it's chemical damage on the pits, on the chips, and we are, or at least we were initially, using the CR39 differently than what the typical physicists have used it. We put the CR39 right in the solution, and so that can cause some damage. Although we have also done experiments with CR39 outside the cell through a thin mylar window, and we still see pits. So I think we have, at least in our minds, we've eliminated the possibility that all of the pits are caused by chemical damage. But the let me see, the pits on the back. We've also been we're challenged on, well, could these be neutrons, or you don't have any neutrons or anything, and when you look at the back side of the chip, you see pits there also. And if you do the calculations, it would take an alpha particle that has close to 40 million electron volts in energy to get through 1 millimeter thick plastic to leave a pit back there. So either we have extremely energetic alpha particles or we have neutrons. If you look even off to the side a little bit, now all of a sudden the energy required for an alpha particle gets even higher. So early on, there was still debate on whether or not you have neutrons. And in fact, I will tell you that there are still people to this day who say they have an alternative mechanism. And we are engaging those people in discussion. If they'll talk to us, we would like to engage them in discussion, in a scientific discussion. And we've structured a couple of experiments to see if we can address their concerns. So anyhow, right now I think where we stand, I believe there is an extremely high probability that we're producing neutrons because, oh, by the way, we've also detected neutrons directly in one experiment. We had a neutron detector there in addition to the CR39, and it detected neutrons that were like 10 standard deviations above background for several hours. So it's a kind of thing that you really can't explain, other than to say that there must have been some neutrons coming from the electrochemical cell. The conventional theory at the time said that all neutrons, would be high energy, and the flux, the amount of them, number of them, would be such that it would have caused been a health hazard to anybody who was working in the area, working around the cell. Now there are various theories and explanations that say maybe these neutrons are not high energy when they're formed, and as such, maybe they're not a hazard that they were. Certainly. Well,
what are you seeing experimentally? You're seeing neutrons, but what are their energies and what are their fluxes?
We have seen neutrons in the CR39. It takes a neutron that's greater than 12 MeV to break a carbon atom into 3 alphas, and we have seen that occurring in CR39. So we know that some of the neutrons, if that's the reaction, some of the neutrons then are at that energy level. We have seen some experiments where neutrons may be in the few hundred per minute range, and it lasts for several hours. We're approaching an area now where we have health issues, but we haven't seen that very often, and so, in fact, we're going to rewind this. This is not my field of expertise. I've talked to people from Sandia about this, and they're the ones that we're looking at. But basically, the kind of the bottom line is, whatever is going on, it's not producing neutrons at the rate or energy levels that conventional theory would have predicted.
Nowhere near it, right?
Nowhere near it. But we are seeing neutrons that are significantly above background, so that it's, I think, very compelling evidence that in fact neutrons are being produced inside the cell. The other thing is, where's the gamma radiation? We're seeing some nuclear ash. We're not seeing gamma, and recently there's been some discussion about is the gamma somehow inside the lattice being converted into heat or other things. So whatever it is, there's still a lot of questions that we don't know the answers to.
All right. It's about 30 seconds left.
Oh, well, what can I say in 30 seconds? Time to eat.
Okay. Thanks, Frank.